Kind of neat, huh? This is something I was thinking about, well, the result of something I was thinking about, and I thought I'd have a little fun today and just kind of show you guys what what was going through my head when I made this. Now, before we go and talk about it in any great detail, let me emphasize the coordinate system we've got here. This is our x-axis right here. This is our y-axis. So normally we're up here on the z-axis looking down, and we're normally seeing an xy plane involving these two axes. Obviously this is three-dimensional, something a little different than I normally do, but I thought it'd be fun to talk about. Now you might be tempted to look at that particular view and that particular view and say, well, we're talking about parabolas. It looks like I can see a parabola, so we must be talking about quadratic equations. And you wouldn't be completely wrong, but would you believe that I got this figure by thinking about straight lines? In fact, I'm going to tell you that this figure was made from straight lines. Weird, huh? Okay, let's go prove that that's the case. What I'm going to do is pull up a new file, and we're going to do 2D default. Okay, to start with, let me get the window back up here and center it. Okay. All right, I'm going to start with defining m to be 1, and we're going to look at our old friend y equals mx plus b. And specifically y equals mx plus 1, we're going to set our y-intercept to 1. And there's the equation you would have expected, not too spectacular. Well, what I was thinking is, what would happen if we started to graph a whole bunch of these together? Now, typically what we've been doing is we've been choosing that m and animating it. Bring this down a little bit, and then just playing it. So, in essence, the slope is changing in time, and we were seeing these little animations of what the slope does. And all that's fine and good, but I was thinking of something more all-inclusive. Let's examine that. Now I'm going to start by actually turning that line off, and I'm going to use a different kind of notation for my parameter. I'm going to use set notation, which is right now n is equal to the set of just 1. We're going to start with that. And I'm going to put in another new equation, y equals nx plus 1. And we don't get anything much different here, except that I have certain things that I can do with this that I can't do with just calling it n equal 1 without the set. I want you to notice that there's nothing right here. When I change this, we're going to see something pop up over there. Let me say that n is equal to 1, 2, 3. And just like that, 1, 2, 3, I've got 3 different lines. Notice that over here, we've got now this equation y equals nx plus 1 being talked about as if n was 1, 2, and 3. That's in effect what this set notation has done for us. Okay. Let me expand on this a little bit. I can also do something like, let's say, go from -4, in fact, 1, 2, 3, 4. Okay, and here, let me open it up again. You can see it's done -4 all the way up to 4. If I don't tell it what to change by, it decides to change by 1s, and so that's what it's done there. If I were to now go over here and say, well, okay, I'm not happy with going by 1s, I want to go by 0.5 each time, well, it may yell at us a little bit, and I think there's a limit to how high this can go. In fact, I don't think it's a very big limit. If I remember, I think it's like 22 or something. But now you can see we've got a whole bunch of lines. All right. Well, great. I've graphed a whole bunch of lines on the same plane, and what do I get? Well, basically, if you can imagine what happens to all the various lines, because I haven't graphed them all, let me come back over here, and I want to just highlight that real quick as a different color. And if I now play this, you can see, except I'm going to have to click on it, you can see that all that that's doing is sweeping through all of these various values. And so in other words, if this was all black, just like you can see with the gray or start to see with the gray that's underneath it, I would just get a whole bunch of black areas. In fact, if I could let the slope go to plus or minus infinity, all I would do is get a big black square. So not too impressive. However, what if I did something different? Let's go ahead and pause that. What if I graph each of these slopes on their own little xy plane? And what if I stacked up those planes? Let's say on another axis going in and out of the paper. Well, that's what got me to the figure we were talking about. Let's go ahead and bring up another file, a new file. We're going to make this one 3D. Now, typically this is on default. I tend to like my white a little better, so I use that. This is what that screen is going to look like. Let's talk about what we're going to do here. Typically, this axis here is going to be what we call the z-axis in 3 dimensions, and this one will be the y-axis. The one that I talked about going back and forth this way, in and out of the page, so to speak, is going to be our x-axis. All right, let's come back over here. I'm going to move this screen in and adjust it so that it's completely in the window. All right, so in other words, what I was just talking about is I want to see my line kind of going that way. How are we going to do that? Well, I'm going to show you the transformations that we're going to do to our two-dimensional friend, y equals mx plus b. And again, it's going to tell us that we didn't define things like m and b, and so it doesn't know what to do with that. All right, well, here's what we're going to do. We're going to take the old y value, and we're going to change it into the new z value. Okay, and it's not going to like this. I'm just doing this for your benefit so you can see the transformations. The next thing I'm going to do is I'm going to take the old x and I'm going to turn it into y. Then I'm going to take the m, the old m, and change it into our new x. All right. So with that in mind, let me make a new equation. We just said we were going to change the old y into z. Well, there's our z. All right. We're going to change our m into an x. So we're going to type in an x. We're going to change our x into a y. And the b that I had previously was b equal 1. I'm going to stay with that, and we'll see what happens. And there it is. There's that figure. So believe it or not, this is being made or generated from a straight line equation. Well, I know it isn't really what you thought at this point. Where's the lines, you say? Well, I'm going to highlight those and prove to you that this is made of lines. But before I do that, I hate these grid colors. These grid colors can be useful at times, but you know, right now it just is ugly. So I'm going to change it. Going to Inspector, we can change a checkered board into uniform. They typically then jump immediately to default white. I'm going to go with something different than even the other one. I'm going to go with sea foam. Let's go ahead and close that, and there it is. So it didn't take very much to actually generate this, but where are the lines? That's the next question. Well, let's put some lines in. Well, in order to do that, we're going to have to use something that I know some of you hate, and that's these parametric equations. We're going to use Cartesian surface. We have now a three-dimensional version of this. We were using two-dimensional versions previously. When you use both t and u, typically you're doing that because you want a surface. Now, we don't want a surface, we just want a straight line. So we're going to get rid of the u's, but we are going to keep the t's. Okay. Put some spaces in there to see what's going on. We're going to let our t go from -5 to 5. Now, the reasons I'm choosing this is the edges of the graph that's given, although I don't think you can see it from this. In general, there's 1, 2, 3, 4, and the fifth tick mark would be at the end of the arrow. And this is typically what comes up default, so I'm just going to stay with our default size at this point, and so t is going to go from -5 to 5. Alright, now what we're going to do is we're going to let the y value be the thing that's changing. that effectively is our old x. If you remember correctly, we had y equals mx plus b. So we're going to let t go from -5 to 5. Okay. All right, the other thing we're going to do is we're going to let this be an m, and it's not going to be happy about that because I didn't define m previously. But since our x is going to be each of the different m's, the z then is going to be, well, what? X is m, y is t, and then we have +1. So that's exactly what we're going to type in. M, t, +1. Okay. And again, it's going to yell at me because I didn't go ahead and define m to be 1. So, or that, sorry, yeah, didn't define m. So let's go define m equal to 1. Okay. And there we have a line. Check it out. Now, if you look very carefully, and kind of look around, there's no spaces between the line and the surface. It's on the surface. Kind of weird, huh? Very curved surface, and yet there's a straight line that can fit on that surface without bending the line. That's our line. Okay. Now, you may not be completely convinced. You might say, well, I think you're bending the line somehow. I don't recognize that equation. Well, tell you what, let's turn this off. Now what do you think? Straight line or not? What if I can look straight down the line? Whoop, now it turns into a point. Pretty cool. So that's a straight line. No question about it. Straight line, and let's put the surface back on, and there it is. Okay. Well, okay, maybe it's a straight line, but maybe you just got lucky. Well, let's first of all take this straight line, go back to Inspector, and I want to make a little tube instead, and that's going to thicken up the line a little bit. I want my resolution to be a little bit better, just because, remember, you got to hit this little circular button that tells it, go ahead and figure it out as a better resolution. Okay, and now that makes it a little bit clearer that the line is on the surface. It's you can almost kind of look down the pipe. Trying to get it for you there. Okay. All right. Well, let's go ahead now and show you that there's a lot of different lines on the surface. What I'm going to do is do what we did before. I'm going to animate M. All right. Let's pick some values. We want to go from -5 to 5. Actually, let's go -4 to 4. I don't want to go all the way to the edge. And I'm going to stay with 11 values because this might take a little bit of calculating in here. Let's see what happens. And yeah, it's taking a little time to calculate. Okay, it's moving kind of slow. Tell you what, let's see if we can speed up the process a little more. Turn off the tube for a moment. Let's see if we get. There we go. That's a little bit nicer. It's not prettier, but it's nicer. Okay. We can look from different views now and see what's going on as we change M. Do you see any places where the line is coming off of the surface? I don't. All right, let's come back over to the x-axis and kind of turn it this way. You can see that this is basically what we had in the two-dimensional picture, and if I turn off my surface, you can actually see that. There's the line going back and forth. Okay? All right. Well, you still might not be convinced because, well, it might be tough to see, right? So let's see a bunch of lines. We now know how to do that. So let me set up another one of these equations. I'm just copying and supposed to be pasting. There we go. Notice we can use the same variable t, but t is now only going to apply to this equation. Let me hit return. The t that's here is different than the t that's here. The t that's here is defined for this equation and this equation only. The t that's over here is defined for this equation and this equation only. Now what I'm going to do is I'm going to define that n variable that we talked about in the two-dimensional case. And we're going to let n equal, well, let's go for the gusto, -4, -3, dot, 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 all the way up to, let's go to 4. Okay? And what I'm going to do is come over here and change the m to an n there and there. And there, we've got a whole bunch of lines. Okay, let's go ahead and turn off the old one. And now what do you think? Pretty weird, huh? I don't see any lines that are going off of the surface. All right. Now, let's turn off the surface. Here's our x-axis, or our slope axis, if you will. And if I do that, we're looking straight down the barrel of m equal 1, or b equal 1, the y-intercept. So these are all the same lines that we saw when we were looking at this one? Yep, this one. See some similarities? There they are. All straight lines, and they're making up that surface. Let's go ahead and put in a few more. Again, it's going to have a little heart attack because it's got to do some calculating. There it is. That's pretty cool. All right, again, so we're going over to here, lining this up. Just all the same that we saw in the two-dimensional case. But we get a whole different kind of curve when we start thinking about 3 dimensions. Now I put these all in tubes to make it look nicer, and if I was wanting to make a movie out of this, then maybe I'd get it spinning a little bit and let it do the calculating and generate a movie, but I don't really think we need to do that. This is pretty much the end product of what we were talking about. So there it is. That's a straight line. Now, by the way, this equation, I told you that it did have something to do with quadratics, and it's not that it looks like y equals x squared, but it sort of does. If you take y equals x squared, let's say plus 1, which is a parabola that would, in fact, it literally is. Let's see if I can find it. I believe, well, it's no, we're not going to actually see it, but it would have the same shape as this particular parabola that we're seeing, this outline. And in effect, the reason that it's, in fact, if you look at this, this is kind of like in the middle of the x and y, and the reason it's in the middle of the x and y is because that's what's happened. Instead of y equals x squared, we've changed the old y to a new z. We've changed one and only one of the x's to a new y and left the other old x as an x. And so we end up with a parabola that's kind of at a 45-degree angle. If you look, well, I'm not sure you're going to be able to see it, but down this line right here, that is where our parabola is showing up. So this is, in fact, a second-order equation. There's, of course, different parabolas that are showing up there and there, but that's not really what we're studying, at least not now. Maybe later. All right, well, I hope you enjoyed this. That's it for today's video. Let me go over to the final screen here. Today we've been studying how to graph all the linear equations for y equals mx plus 1 through the equation z is equal to yx plus 1, or xy+1, whichever one you want to talk about. Okay, this has been A Tutoring Enterprises. My name is Joe Maciars. My website is at www.tutent.com. I do tutoring online, and I do tutoring in person in Lincoln, Nebraska. So if you need some tutoring, give me a call at 402-421-3536 or shoot me an email at tutent, T-U-T-E-N-T, at neb.rr.com, and we'll try to get you set up. The website has all the good prices and times available and that kind of thing, so check it all out. And that's it for today. I hope you enjoyed it, and thanks for watching. Feel free to hit that little like button down below, and have a great day.